All right. Good morning, folks. Hopefully everyone's okay. I know a few of you are off taking your a few AP exams today. So please make sure that, and I emailed those folks. If for example tomorrow you have an AP exam, just respond, let me know, and then try to make sure you watch the video for tomorrow. And like I had mentioned yesterday, yesterday over the weekend, I pointed out that what I would like to do, wrap things up today, tomorrow, Wednesday. Then no lecture. Just try to keep chemistry out of your mind. Don't think about chemistry. Just kind of relax as best you can. Do whatever else you have to, and then on Thursday, go ahead and take go ahead and go in, take the exam, knowing that you'll do fine. And then what I would like to do then is on Friday for our class, I'd like to meet live on Zoom. Not so much to talk about anything that's chemistry related, but just to kind of get caught up, see how you folks are doing, and then get your impressions of the AP exam. Like I had mentioned on the weekend, over the weekend lecture, I typically meet with folks after the AP exam, and then that way then we kind of go over the exam, talk about it, and kind of just unwind, kind of debrief you a little bit on what can happen. But then and then you'll be free to go. Okay. So hopefully I'll get a chance to see some of you folks, or if not everybody, on Friday, and then we'll get caught up. Okay. All right. So with that said, though, let's quickly. I want to finish up with the Beers Law today. So I want to go ahead and do this with Beers Law. And like I said, this afternoon, I will go ahead and cover Chapter 10, the material that you'll need to know from Chapter 10. Please take a look at Chapter 10. And like I said, after the AP exam, what I'd like to do is continue on with Chapter 10 and start to cover some of the material that aren't necessarily covered in the AP exam itself. I want to make sure that I give you a good foundation for what you'll see on the AP exam. And then after the AP exam next week, we'll continue with Chapter 10 and cover the material that you'll need to know for this class moving forward, and for the science classes as you go forward with your careers. Okay. All right. So with that said, then let's talk about the spectroscopy. Okay. We finished up with the discussion of photoelectron spectroscopy. Now, that was a spectroscopic technique that took advantage of the photoelectric effect. It took advantage of hitting a molecule or an atom with high energy photons. Those high energy photons then forces the electrons to be ejected from the molecule or from the atom. And based upon the energy that those ejected electrons have, we can deduce the ionization energy that was needed, and thus that ionization energy correlated back to the binding energy of these electrons. And based on that, we were able to get a basic structure of the atom or of the molecule, and that's where the electron configuration was. We were able to deduce the electron configurations from. So we were able to obtain structural information. Now, this is energetic structure, obviously, not the actual physical structure of the atom, but we were able to locate and define the locations of those electrons in terms of their energy. So we're able to kind of get an idea of we're able to get a picture of what the atom and the molecule looks like. And that's what spectroscopy does for us. And so what we're going to look at here when we start examining visible light spectroscopy, and that is we can also obtain information about structure using visible light. And actually the spectroscopic technique here is known as UV-Vis, meaning UV and visible light spectroscopy. Okay? And so what we do is we were able to get information about structure as well using UV visible light. Okay? The light, the energy, the electromagnetic energy encompassing visible light all the way up to UV. So from red all the way up to blue and into the UV range. And we're able to obtain structure from. Now, obviously, the structure that we obtained for the molecule has to be put together. We get the puzzle pieces, like I said. Spectroscopy provides us with the pieces of the puzzle. We still have to put the puzzle together. Okay? And so if you take a look at this here, this is an image of a UV-Vis spectrum of 3 different compounds here: benzene, naphthalene, and anthracene. And so what we have here is that each one of these molecules then will absorb UV visible light in a different way. And so when we talk about UV visible light spectroscopy, we're talking about the absorption of the energy, absorption of that energy, and based upon that absorption of that energy, we can then deduce some things about the structure of the compound itself. Now, arguably, you could say then that photoelectron spectroscopy was also absorption spectroscopy, and that is the atom or the molecule absorbs the incoming photon of energy, and once that energy is absorbed, the electron is emitted, okay, and then we can make our conclusions about the energy of the emitted electrons as well. So spectroscopy is about absorption and emission, okay? Absorption of energy, emission of energy. And so that's what we will look at here with spectroscopy. Okay, so whether it is a UV vis spectroscopy here, or when we talk about visible light spectroscopy and Beer's law, we're talking about the absorption of energy. Okay, and so what we do with that is going to allow us to determine then whether we're going to use the spectroscopic data to determine structure, or use that quantitative data, that spectroscopic data to do other types of analysis, specifically for our purposes here, the quantitative analysis of a solution. Okay. All right, so we'll get to that in just a moment, though. But the study, so what we're going to do here is spectroscopy then hinges upon using electromagnetic radiation, okay, and the absorption of that energy in order for us to deduce some key facts about the structure and about other quantities and about quantitative data regarding that particular molecule or that structure. Okay. All right. So with that said, then with the spectroscopy here, this is an example of a UV vis machine that you'll probably use. Many of you will as you go on. You may not use this until you get to organic chemistry, but essentially what happens is here, you put the sample, you lift up this cover right here. So you lift up this cover on the left-hand side, you lift that up, you put your solution in, you typically have to make a solution. So remember, a solution is a homogeneous mixture. So you take your compound, you add it to a solvent, and you mix it up, okay? And then you put it in here. There's a chamber inside here. You put your little container, which we refer to as cuvette. You put it in here, and then you turn it on, and then you get your data. Okay, and so this is an example of a UV vis machine that that you'll use probably in the first experiment or so of your organic chemistry class. Okay, but what we would have done in class is that we would have done something similar here using what's called a photospectrometer. Okay, so this is a picture of a photospectrometer that we have in class. I want to make, I know this is something thinking a little bit forward, but, for those of you who are interested in how this experiment's run, it's a very cool experiment that we would have done in class. We make a solution of dyes, and then we go ahead and we use it to determine then concentrations. But this is a spectrophotometer here, which is different from the UV vis one that you saw in the other one, where this one just basically allows white light to pass through. And then what we do then is we use that not to obtain information about structure, but to obtain information about concentration. Okay? And so what we do here is we're going to use this spectrometer here in order to photospectrometer here in order to obtain information about the amount of a particular molecule in a solution here. Okay, so what we do here then when we do this spectrophotometer here, we make different solutions. So these are different solutions here, different dyes. So we make a solution. We add in our solution. We dissolve our molecule. We dissolve our compound in a solvent here, and then we put it into the spectrophotometer here. Okay, and then what happens is with the spectrophotometer, what we're doing is we are going to analyze quantity. Okay, so this is a quantitative analysis of a solution, the quantitative analysis of a compound. Meaning then, what we're going to try to do then, when we do quantitative analysis, what we're doing here is that we're examining amounts. Okay, we're studying amounts of a substance and how much we have of it. Okay, so amounts, and so we're asking the question then, how much, and through this particular analysis, we can answer how much here. So essentially what we're doing here is not obtaining information about structure, we're obtaining information about concentrations. Okay, so what we're going to do here then is we're dealing with concentrations rather than structure. Okay, so make sure you keep that in mind. It's a key difference between what we did in the last section with photoelectron spectroscopy, and we dealt with structure. Here we're going to be dealing with quantities. So this is a quantitative analysis rather than a structural analysis. Okay? So visible light can be used in order to do this. Visible light can be used in order to determine quantities. Okay? The reason for this then is that certain compounds will absorb light at different frequencies. Okay, so remember, visible light comprises a set of colors, Visible light being the light that we get from the sun, the light that we can see. Okay, the energy that we can see is what we refer to as visible light. And so if you notice in the first container, we don't have anything, light passes straight through, okay? And then what happens is that as we add in, so in this particular experiment, we add dyes in to each one of these cuvettes. So this is known as a cuvette here. We add in dyes, and the reason why we see these dyes here is because the dye is a particular molecule. The dyes are molecules that will absorb a certain amount of light. And what we see then is not the light that's absorbed, we see the light that is not absorbed, the light that is reflected off the molecules. So the molecules then will absorb the light. The light absorbing component of each one of these dyes, okay, so there is a certain component of each one of these dyes here, each one of these solutions, okay, that absorbs the light. Okay, this light absorbing component is what we refer to as a chromophore. Okay, and maybe if some of you have come across this term before in your bio class, but a chromophore is essentially a molecule, okay, a molecule that or atom or group of atoms that essentially is going to absorb light. Okay, so if you can imagine, I think this kind of serves its purpose. It's kind of a good example here. The chromophore then is if you think of it as a baseball glove, and that light then and electromagnetic radiation and more generally, but light then as a series of baseballs, and this fits with the proposal that Einstein had pitched, and that is that light is made up of photons, particles, okay, that travel through space, And so if that's the case, then these particles then will hit the chromophore, okay, hit the baseball glove, and you can catch these light particles with the glove, okay. And so what happens is the chromophore is a molecule, group of atoms, or an atom or a group of atoms that can absorb, that can catch these particles here, okay. And as it does so, it's going to absorb, the electrons get excited, and then it drops back down. Okay, so that's what we see there. Okay, so that's what chromophores do. Chromophores will go ahead and absorb light. Okay, and so the light that you see then is not the light that is absorbed. So you can imagine the leaf plants. Then the leaf plants has certain chromophores. There are chlorophyll A, chlorophyll B. And each one of those absorbs different wavelengths of light. Okay, and so the absorbed light that you do not see, you can't see that, but the light that is reflected, the light that is not absorbed by the chromophore. So the leaves have certain chromophores, and the chlorophylls, the different chlorophylls, serves as chromophores. They absorb certain wavelengths of light, and so the wavelength of light that is not absorbed is what you see. Okay, and so with that said, then what you see is the light that is reflected. The chromophore is the light. The chromophore absorbs other frequencies of light. Okay, and so we will take advantage of that in order to carry on with Beer's law, and we'll get to that in just a moment. Okay, but before we do, let me just go ahead and point out here then the different molecules here. So we saw then benzene, we saw naphthalene, and we saw anthracene here. And so each one of these also will absorb a certain wavelength of light, and I give you the wavelength of light here. Benzene absorbs at about 210 nanometers, naphthalene absorbs at about 220, and anthracene absorbs about 250. They absorb light at that particular wavelength. And remember, based on what we learned back in chapter 5, we can calculate for the energy. We can calculate for the energy and thus the particular colored light that is absorbed by each one of these compounds simply based upon their wavelength. And so make sure you remember how to do that. Okay, but what we see is that each one of these has slightly different bonding interactions here. We refer to this then as a repeating pi bond structure here. Okay, and so because of that, they will absorb light slightly different. And because of that, we can differentiate each one of these molecules here. But we want to be able to take advantage of the light absorbing abilities of these compounds that we want to examine, okay, to determine how much of them we have. Okay, not so much determine structure, but determine how much of them we have. We can do that. The spectrophotometer does that in a really cool way. Okay, so let me just make sure I refer you back to the couple slides back to that little black square box. Okay, that's called a spectrophotometer. And what a spectrophotometer does, and I just want to go over the different parts here real quickly for you, because we use the spectrophotometer and the information that it gives us in order to determine concentration. Okay, so how do we do that? We'll talk about that right now. Okay, so in the spectrophotometer, we have a light source here. This light source then is typically a light source that is white light. The white light, remember, all of the frequencies of light are wrapped up in white light, meaning all the colors of light are represented in white light. Okay, all right, so you have the white light. It passes through what we call here collimator, okay? Collimator, sorry, a collimator. Okay, so it passes through this. This is essentially a, if you want to think about it, if you ever you've seen like a magnifying glass, this is what we refer to then as a convex lens. In physics, we refer to this as a convex lens. But what do magnifying glasses and convex lenses in general do? If you can imagine then, as light passes through one side of the magnifying glass, on the opposite side of the magnifying glass, what happens is that light gets concentrated on a single focal point. So what the magnifying glass, okay, and what these collimators do in the spectrophotometers here, is that they concentrate light. That means they take the beams of light, and you have to imagine this here, all light travels essentially from the source outwards. All light travels from the source outwards. And for those of you who've taken physics, I think you've gone over, hopefully you've gone over this section already. They all are basically parallel. So the light rays are traveling parallel with one another. What these lenses do, what the collimator does, and what magnifying glasses and convex lenses do, is that they take the light rays as they're traveling parallel to one another, and they concentrate them in a single point. And that's why we're able to take advantage of magnifying glasses, because on the side where the light beams are concentrated, they all are focused on a single point, and thus we call that point a focal point. At that particular focal point, the beam of light is intensified, so much so that it's very bright and it's very, very hot. We know it's very hot because if you've ever placed your hand on the opposite side, you can feel the heat being generated by all those light beams being concentrated on a single point. And so in a spectrophotometer, that's what it does. So the collimator, go ahead, what it does is it focuses light into a monochromator here. And what the monochromator here does, and if you've ever played with the prism, you'll recognize this well. What the monochromator does is it splits the wavelength. It splits the wave into different colors. Just think of a rainbow. A prism, then light can pass through a prism. And if you've ever played with prisms, the most difficult part is trying to adjust the prism in just the right way where you can get the light and you can to pass through at a particular angle, and then you get the rainbow. You get the prism. Okay? What the monochromator does is it's a prism. So the collimator concentrates light into a certain point on the monochromator, and the monochromator then splits the light into splits the white light into different colors. Okay, and when it does so, that light then, now if you notice, it splits the light. We have all the different frequencies of light here. We get to the selector here. Okay, what the selector does then, as the name implies, is that we can adjust the selector here to obtain different frequencies of light. We can obtain different frequencies of light as we need to. And so in this example, we allow, and so what it does is it allows certain colors of light to pass through. Okay, and so it passes through, and then it hits our sample. Okay, this light here, this is what we refer to as incident light. Okay, this is, so I sub naught is known as incident light, which is the light that is the light beam, the light that before it passes through our sample. Okay, incident meaning that it's moving toward the sample, it's moving toward the particular object from the source. Okay, so incident light is always light from the source. Okay, so let me go ahead and write that here, light from the source. So incident light, and the term incident is always going to be referring to from the source. Okay, so incident electromagnetic radiation comes from the source. Okay, so incident means that it comes from the source. Okay, so there we have our solution here. Okay, we have our solution in a cuvette. Okay, and what we have here then is this is the transmitted. This is the transmitted light. Transmitted light, okay, is light that passes through. Okay, so you want to be able to differentiate between incident and transmitted light here. And I'm running out a little on, I'm out of time here, so I'm going to continue on with this after in the afternoon lecture. But those are the two amounts that we want to be able to compare. We want to compare the amount of incident light to the amount of transmitted light, because they should not be the same. So you have a lot of energy going in, some of the energy going out should be less. Okay, and so what happens is then the transmitted light reaches our detector here, and the detector then sends it to the processing unit, and it gives us a reading. Okay, what this number is right here, is what we will use for Beer's law. Okay, so we will pick up with this discussion then after school today, and then we will do a calculation using Beer's law and this number here. Okay, all right. So I will see you folks this afternoon. Okay? Have a good one.